for the operating system, so we are keep going talk about the processor, and also we are about the threads. So we need to know the distinction between the process and threads. So we need to follow what's the define the properties of it. Okay, so far, if you know, so the basic idea is that several components in any complex system will perform particular subfunctions that contribute to the overall function. So as what we know, so it's the OS. And based on this one, for process, we have the, two characteristics. So one is called the resources ownership. So for the process, includes like a virtual address space to hold the process image, and also the OS will provide protection function to prevent unwanted interface between processes and with respect to resources. That's what we are doing, like when we doing some exercise, discuss like how to this example, like we say we have limited resources, how the different processes are allowed to access it. Then we do have a hunt or like a waiting function or sleeping to get a chance. And as a follow-up, then we need to know like how is like schedule and execution. So we will follow an execution path that may be like interleaved with other process. So a process has a like execution state. If you still remember, we have normally have a like, if our old school have two, and then nowadays we talking about five, like from new we're running, ready, execute, stop, terminate. And then we are more like have an interval, and then interval we have different queues. So for this, and also we will have they call that dispatching, priority, and the schedule and dispatch by the OS. This is what the process doing. And for the process, the unit of the dispatching is referred to as a thread or a lightweight process. And the unit of the resources ownership is that referred to as like process or like a task. And when we say like multi-threading, so the ability of an OS, say to support multiple and concurrent paths to execute within a single process. So like within one single process, we can multi-thread, and then for those threads, we can like they will divide it like different parts, so they can run it concurrently. Okay, so if we look at the map right here, so here's a called a single thread approach. So as a single thread of an execution per process, which like the concepts at first not recognized, or is referred to as a single thread approach right here. So if you look at the maps right here, like one process will be one thread. So when we run it, or like we have like let's say the one process, and then but we have like multiple thread. So you see like when we treat the process like it's a one box, can be the program, or sometimes we say the application itself can be a process. And inside the process, we can just like if we say it's one, that means one process, and one thread, that means we need to load it to one CPU. Okay. When we execute multiple processes, they are also like have only one thread for them. So if I need to execute, that means for one core, I need to finish this one, then I will execute another one. But if we have like multiple processes and multiple threads right here, that means it's more like happening in reality right nowadays. So we have multiple programs execute like for multiple cores, and also when we have multiple threads, like for one single process, then it will like handle like their own threads and like share it and execute concurrently, like maybe by multiple cores. So Mac talks is a very nice example, like one system on one process. It's really hard for you to imagine like, how come it's doing. If we are saying it this way, you can just imagine it. You try to open a web browser and also let's say open the PowerPoint. So if we are only one process and one thread, that means when I open the browser, I cannot do any other action. So when I double click the icon of the let's say Chrome, so I will load the Chrome. Can you in the meanwhile like open another things or like maybe let's say if a web browser you open playing the YouTube, or like you open Spotify listening music, and then can you do something else? No. What's actually happen is that you, let's say if I have called the music, Spotify, and then I have a website like playing video and or like looking for page. So if for single thread and then for one core, one process, that means that I will load the web browser, I will finish it, then you won't able to listen any music simultaneously. So nothing, no sound at all. So once you finish the loading, like execution of the website, then they will start to run the music. So once you play certain time, like finish the time, I will switch back to the website when you have something like to execute. They'll go back to the process. So you won't like things working like simultaneously, or like you won't seeing that you can do multiple things called multitasking. But if you have one process and multi-threads, that means that, okay, I taking the website, maybe we have one is like, okay, I can viewing for video, ping sound, and then showing the graphic animation, like everything. So if I have focus, and then I can translate um, 4 threads, then you are able to like do them simultaneously. Let's say you need to send a printing job, and then you also need to view something, play music. Yes, you can do them in the same time. If we're multi-threaded. And then when we have multi-thread and a multi-program, then we're switching. So if you like from other previous example, if you know sometimes when we are switching the processes like scheduling. Also, when we're multi-thread, then we'll finish this part and then go to process B and then finish the threads, and then go back C, D, go back to A, like this. So that's how it works. So when we change for nowadays, right now, like the right half is nowadays, there's skip like expanding. So it's like depict the multi-thread like approach. So Java runtime environment is one of the system for like one process with like multiple thread. And then if you look at the classification right here, so if we for like only one process, and then there's only one thread, or like for one address space or like this, then we have like MS DOS or like early Mac OS with like this. And when we have like multiple thread but one single USC like Java, we work like this pilot. And then when we go to we take like multiple space and multi-process like with one single thread will be traditional like Unix system. But nowadays, like when you're using Mac OS, Linux, Windows, and to like nowadays 10, 11, all this. Actually, all the operation system are running under like multi-process and with like multi-threads. This is working. So they like what we see like one or many address space, or like one or many threads they put it, this is what you see. This like for the real operating system having. Okay, for the process, the unit of the process, or like we say the unit of resources allocation, and the unit of protection about it. And then also, we have the virtual address space that I host the process image. So you will remember, like when we talk about what's process image, if you recall the about the previous slides, like inside we have a PCB, all the state information, all the data. So that's all this. And also the protect the access to like maybe the memory file or the IO resources, because when certain processes like using certain IO, then we try not to let others to read it, because they will, let's say if we have two processes they're required to access the IO, the input from keyboard, let's say like this. But if without protection, because like for the input, suppose the user inputting is like maybe for specific application, and like or for process A. But if you don't protect it and then let the process B to access it, then they will take the wrong input. So like if it's a minor things, maybe just like some input or different input type, it's just a handle. But for if without like well-defined process, then it may cause a crash. So we need to be aware of it. So that's how the OS try to protect it. Okay. So for one or more threads in the process, so thread execution stage, we have same with running ready. So it's the same, like etc. Also, we will save the thread context. If you still remember process context, we will be the same. It's just because like thread and the process like have similar or like breakdown part of it. So you can see like all the terms or the like vocabulary like using really same. And then execution stack, each thread needs like separate run, and then per thread stack or like dynamic storage, and also all the resources and memory is shared. So that's how it works. And next, about the threads versus the process. So if you look at here, will be, let's say it's a single thread with like multi-threading process model. So for a single thread process model, right here at the left-hand side, we have the PCB user address space, user stack, like kernel stack right here. And but for the multi-thread process model, we have more than, okay, so the basic you will see compare, we have the same PCB and user address space, but we are not for one single thread, we just need to have a user stack or kernel stack, and that's it. But for multiple, then we will have a we need to create a thread control block. It's like same. So like same as like PCB itself, and then for the thread. So it's like minimum version. Then we have like thread control block TCB. And also we put the inside each of them have user stack and kernel stack. And another thread have their own TCB and then user stack and kernel stack. Really so far so that. Okay. So it's a really similar structure, but we changed the user stack to like multi-thread right here. Then it will apply in the like single thread with like multiple the one process with the multiple thread. And then so far why we need to create, because we are using already in reality, or like when you get your own OS, then you already experience, like you're basically really experience all those, like taking those benefits. So the key benefits of the thread driven from the performance implications or of less sharing resources. So it takes less time to create threads than process. And we have like less time to terminate. So of course, like when we make a multiple thread, then we don't have to execute the whole process. So we like execute like breakdown, actually, just like breakdown like small pieces. So when we just like handle execute small pieces, then it will be finished earlier. And so like less time to switch between two threads, like really is it much. So also we can enhance the like efficiency, like we can share the memory communication because multiple thread are using same one access to it. Then we don't have to always like loading from the memory, or like sometimes if with the limitation, if we use still remember like memory and then second memory is that we say the storage, we keep loading, not enough space. So multi-threading, executing, then we share it. So it's way better than that. And also the thread used in a single user system. So this one is all of it, but just need to know like the foreground and background work, a synchronized process, speed of the execution, and modular program structure. So like this, okay. Well, threads like in an OS that support the thread like when we scheduling and dispatching, so it's done on the on-thread basis. So like we can suspend a process involved like suspending all the thread of a process. So now termination of a process, that means that we will terminate all the threads within the process. So we need to know, like remember this two part when we do the suspension or terminate to a process, it will affect the other thread belongs to it. So if you still remember the box right here, so let's say if I terminate this process, then all the threads inside will be affected. So when we terminate this process, all the threads will be terminated or suspend. So just look at the picture, remember this one, they are like under this process. Okay. And then here, if we look at the here's the graph like multi-threading on the unit processor. So like within the time we have like thread belongs to process one, we have like, let's say we have the third A, B, and then process two at C. Let's say for A, we like in the running stage, and then when they ask for the IO request, so we apply it. So if you still remember the 5 state of it, so like from new, from then we get ready, then we go to running. Running, if we finished, we will like terminate or like we block for the IO request. Like sometimes we call the interrupt, whatever. Just like we say from the time, maybe your config why is running is not start because we just like capture from T equals to N like this at this moment. So we always have assumption. So let's say the thread is running, so we're waiting for IO request, and then we just like block it. When we block it, just wait until the request complete, then we go back to the ready stage. So when you ready to execute, then we will just like go back to running, and then once it expires, then we just put it back. Okay. Then when you're looking like when we here, let's say we are ready, then this is running, we are ready and waiting. And then when it's waiting for input, then we just like execute. Okay, so you see this time like quantum expand for scheduling, we always set the time for all the process, or like right now if I like they have a limited time. When they finish, I put it back to running. And then when the process in this moment, it we create the process like the thread C for the process 2. In this moment, let's say thread is executing, and then for process thread 3 is already like finished the time, so it's like waiting. Okay, so because based on this mechanism for the new one, it will execute after this one. So execute finished, but this one already waiting, then I will execute the third C. Then maybe from the time goes back, maybe H is not yet complete. Then maybe depends on which mechanism we are using. Maybe we'll like go back to B, or something like A, B, C like this. Just go back, or let's say A already complete, then we just like switch to B. So for this one, it's like the further, but just like for this graph, it's just letting you know how the thread is like working for the unit processor. And then the third synchronization. So it's necessary to like synchronize the activity of the various threads, like all the threads of a process share the same address space and other resources. And also another things like as the alternation of the resources by one thread affects the other threads in the same process. So we need to know. That's why we need to like do the synchronization. Okay, so here we review the process, like the process and the fact. So just step back once again, and then we will discuss why the process and then why we need to do a fact. Okay, so in the purpose, we in the old time we have a unit processor, and the old time we just like we need to thinking just it's like a batch. So we only do one job for one time. Then our goal is like, okay, for the OS, our final question, how can we do multi-programming? There's like running multiple applications concurrently, and also doing the protection. We don't want to like back application to crash the system. We don't want to crash it. So try not to use the existing like OS to think about this. Just thinking really like long time ago. Okay, then we need to think, okay, for the solution, then we try to create a process like unit of execution and allocation. And then we have the virtual machine abstraction, like give the process like illusion it wants, like machine, like CPU, machine, the IO device, like multiplexing. Okay. So this like we move on. And then but we will have a challenge like about the process creation and switching, like it's so expensive. Like when we need to keep on switching the process like this, and needs like concurrent within the same app. Like this, like also like web server. So I as a local host like computer, I need to do concurrently, but also if I send to server needs to, so everyone needs to do that. Then how about can we do something on top of like the process? Then we start to the third like decouple like allocation and execution, so we can run the multiple thread with the same process. That means that I keep the time to process A or process one, I say, then I have like thread A, B, C. and I can execute it in the same time. So break down to multiple small pieces. Then we can share the same memory. I don't have to rewrite again and then finish all the job. So how about doing this way? So this come out the idea. And then right here, let's say we just like put it in the process. Let's say we have a process right here and the resources which belong to, like we have the memory, we have the stack, and then we have the IO stage, like file, socket, context. Okay. And all here, like in the OS, we still like CPU stage, like PC program counter, like this, the register, all this, like. And also like sequential stream of instructions. So when we put the instruction right here, we load to the memory too as a process. Okay. So when we all this, when you look at it, this one is a structure, and then we have multiple process, or like if just thinking is a multiple applications. Okay, from 1 to n, so multiple of them. And then the OS will be doing the scheduling. So the CPU schedule, so schedule, and every time, actually it turns out we will send one process like at the time to the CPU, like it's the same. So for the switch overhead, it's always so high, but the CPU stage always low. And then memory stage always so high when you're executing. And then for process creation, also it's really high too, always like creating it. And protection CPU, yes, we do it. And then we have the memory IO, yes, we do handle it. And then sharing overhead, yes, it's really high and involve like at least a context switching. That's how we like the process. Then when we see the CPU, I try to switch from the process to process. Okay, see, let's say I have a process right here, and then the operating system and process P. So you see like P0 and P1. Okay, let's say I'm executing. Okay, right here. So we system sometimes if we get the like certain time get interrupt or system call, and go here, I will save a state to like PCB0 and keep running something, and then I will be, and then this one moment like the P1 is still idle way. So it's like no state interrupt and go back, reload the state from PCB1. So I'll get it back and executing, and then within that time you see P0 is there, is idle, so it's not doing anything. So after we executing the P1, the process one, then we will, okay, let's say this one, we'll save it, put it back, we get the interrupt, or we say we get the system call. So we will save the state of PCB1, and then we will reload or restore the state of like PCB0, and then we'll put, so this moment P1, the process will be idle, and I will go back to execute P0 again. That's how we call the context switch. So the code executed in kernel above is overhead. So overhead has a minimum like practical switching time. So that's how actually like all the process switch from another process. That's how it works, like the PCB. Okay. Then okay, we talk about just like process, and then you will remember the also the facts, right? Okay, so inside fact, so we will have the like different pieces right here, and then we have the also we put the serial state. So you can see the difference compared with our previous photo. So here's the single one. So see a serial state, a memory IO state, and then when you look at the thread right here, thread. So here we will have each one have their own like CPU state with the same, like the memory and IO state will be same. So like from P1 to Pn of this, and also we will, all of them actually same. We will send to the CPU scheduling, and then the OS handling it, and then it's the same. The base also like hardware, everything actually is always the same. Then it's like right here in the software application. For the switch overhead, okay, so mainly it's only the CPU state, and that's it. So compare is like it's low of the switching overhead, and then third correction also is low. And then the protection we still yes. For memory, I open it no, because we need to share it, and then sharing overhead is still low because the third switch overhead is really low. So you can compare the difference like with the table right here. low, low, and then yes, no, low. And when we look at this one, always say CPU stay low, but when we the switch overhead say high, high, and then process core is high. And for all the processing, yes, yes, because we are not sharing the memory IO, okay. And then for sharing overhead, yes, it's so high. So you can see the differences between like process and the effects. Okay, so there's a reason why we try to like after we create one process and then on top why we like try to say okay try to build the like the effects like help us to reduce. Okay, then if in this moment like in this one will be closer to the reality. In the reality, we will put all them together. So all the process we have like multiple threads. So each of them like the same structure. And right here we will change and we have multiple cores. Let's say we have 4 cores, so 4 threads at the same time. So we can like switching say to and execute at the same time. So we can making the like he's saying the switch overhead or like only the CPU stage. And this is so it's low, like third correction also is low protection. CPU, yes, we do it. Memory, no. So you see like sharing overhead is low, same. Just like first switch overhead because low, so it's so-called over sharing overhead is really low. So you see everything right here. So after we shrink, so multi-threading, so we can execute all these like 4 threads like in the same time. So CPU switch like from thread to thread, like thread switching is the context switching from one thread to another in the same process. So the thread switching is much like cheaper. So we need to really remember. So the resource level switching, the cost is below. So only we improve switching the processor state, like PC and the register. So generally it's really efficient. Okay, so you know. Okay, so the life cycle right here we talk. So you see when we get the new and then you will say get emitter, so we put it in like ready and ready. Sometimes we will try to put it to running, so schedule with dispatch it. And depends on if we get the interrupt, if you remember the graphic interrupt, so we put back the ready. Depends on if we finish, then we just exit with terminate. But sometimes if we need to get like the system call or the interrupt event, then one like IO or event, so we will like put it back to waiting. So we get the queue and somehow, and then once the IO or some event complete, we put it back to event. The ready state. So we just need to waiting for the like for the OS to like for the scheduler dispatch it and it goes back to running. So you see it's really similar as a process, like it's just like inherited it. So in the new state there is being created and then ready. So it's the waiting to run and then running is the being executed, waiting for some event to occur, and then for terminate, so it will finish execution like active threads are like represented by the like TCP. So it felt like kind of block. So it's like control block and then TCP is like organized into queue based on their state. So far would be like this. So here that everything like two separate like independent will be responsibility of a process and the fact that like time slice management versus context like switching and then memory management and also files versus like handling and like all this like resource allocation protection and also the reserve execution and scheduling. So you can know but you can look at it. And to of you can think that in a multi-thread environment, if a process is defined as a unit, the resource allocation of a unit protection. So let's say, so to have a protection and also process switching overhead can be high compared to the thread. So you see, if we look at it, so we remember the thread thing is always a lower overhead. Okay. Over here we just like skip part of it. So in here we'll cover the last part of the types of thread that we will finish like for this class. So mainly for the types of threads, we'll be like able to expand the difference between user level and kernel level threads. Okay, user level ULTs. So for the ULTs, so all the threads managed is like done by the application itself. So if for user, if you still remember, like the kernel is more like handle the hardware. It's a bottom layer between the hardware and application. And then for the application, just like need to let's say into the kernel. So that's how it's done. So the kernel is then aware of the existing of the kernel. So you will see. So kernel space right here, the first library, the user space right here. So kernel, they don't know how it's like actually doing. So this one is for the user level facts. Okay. And we try to see here like the relationship between the ULT. So that if you still try to remember this part, so that like the user level, one like the current only and multiple. So when we go down, so let's say for the third one, for the ready warning, and then the stage like we make it simplified. So we say ready warning and block, and then execute like third two, and then we have another like process speed like right here, and then switching, and then this one ready, same running, third one, and then third two running, execute B like this. So you will see like right here multiple. So here's an example between like all the like third stage and then process stage. So you see the process is running, and then first one here say the process B is running stage, and then when the process B is blocked, but you can see that it's still like third one maybe ready, still running, and then put it back to ready, they can still execute running. So you see, even it executed, you can have different stage. So maybe process go back to running. So third one maybe ready, put to running, and third two then block at this time. So you can see there how it works. So for the advantage of using the URTs, so you see that threading switch does not require the kernel most like privilege. So we do not need to do it like to mode switching to do the management. Schedule can be controlled by application. Possible like use different schemes that we can run in any OS, because we don't have to. Remember, the OS is helping us, and also the kernel is helping us. For the hardware, we say the Intel CPU, and then maybe the AMD CPU. Maybe nowadays we have like Apple, they have called the silicon, the M1, M2, M3. Also we have that for ARM. So we have different system. On the OS that running web kernel. So for our application level, when design, we do not need to how actually the kernel works. So we do not require about it. So these are benefits that we need to just like design on the user level, and that's it. And for the disadvantage of it, so in the typical OS system, that makes it of course like a block. Okay, so as a result, so when we like block, so like you have to execute a system call, and not only is the fair block, but also like of other effects within the process a block. So here's the things, because on the top layer, so if you remember top layer, so multi of it. So when in the kernel level, they have blocked all of them, they already block, we stop. So because we don't know, we need to wait the kernel finish it. So here's the disadvantage. So in the pure UOT strategy, so multi-threading application cannot take advantage of like multi-processing. So you say multi-threading and then multi-processing is not really working together. So we need to overcome this one. And for this one, for the rest, I will keep on in the coming class. And thank you for this one for today's class. And that's it. Thank you.